It's a beautiful day in this neighborhood, a beautiful day for a neighbor. Would you be mine? Could you be mine? It's a neighborly day in this beauty wood, a neighborly day for a beauty. Would you be mine? Could you be mine? I have always wanted to have a neighbor just like you. I've always wanted to live in a neighborhood with you. So let's make the most of this beautiful day. Since we're together, might as well say, would you be mine? Could you be mine? Won't you be my neighbor? Won't you please? Won't you please? Please won't you be my neighbor?
Oh, hi. Sorry, didn't see you there. How's it going? Good evening, everybody. Welcome to Tibbetts Physics. What is crappin' in? Today, we are going to look at two problems from your textbook. The first problem we'll look at from Chapter 2 is number 19. 19 reads, Runner A is initially 4 miles west of a flagpole and is running with a constant velocity of 6 miles per hour due east. Runner B is initially 3 miles east of the flagpole and is running with a constant velocity of 5 miles per hour due west. How far are the runners from the flagpole when they meet? This is an interesting problem. Why don't we first just draw out what's going on? So here's our flagpole. We have two runners. Runner A, we're told, is 4 miles west of the flagpole. I know these aren't the appropriate units that we use in this class, but we'll stick with miles and miles per hour. So let's say D sub A is 4.0 miles west of the flagpole. Why don't we put a negative there? So negative 4.0 miles. And their velocity is 6 miles per hour due east. V sub A, 6 miles per hour. And they're going east. Runner B is 3 miles east of the flagpole. That's positive, so D sub B is 3.0 miles. And they're going 5 miles per hour west. V sub B, since they're going west or to the left, let's put negative 5.0 miles per hour. So the question is, where are they going to meet relative to the flagpole when they run into each other? We have a couple of ways of setting this up. We learned earlier that V is the slope, the velocity is the slope of a position versus time graph, where D, their starting point, would be the y-intercept. So let's just look at this as if it were a math equation, y equals mx plus b. So if we look at runner A first, we could say that y sub A is equal to m, that's a slope, which is 6 miles per hour, times x, plus their y-intercept. In this case, their y-intercept would be negative 4.0 miles. Should have an I there. If this were a distance or a position versus time graph, our x represents the time. That'll be when will they run into each other. And then same thing for y sub b. We'll get negative 5.0 miles per hour. Plus, or times x, plus 3.0 miles. And since we want to figure out where they run into each other, we can just set these two equations equal to each other, because they will intersect, and that's what we're trying to figure out. So let's do that. So 6 miles per hour times x minus 4.0 miles equals negative 5.0 miles per hour times x plus 3.0 miles. We'll combine our x's, so we'll add 5 to the other side. That will give us 11 miles per hour times x. And let's add 4 miles to the right side, leaving us with equals 7.0 miles. From here, we'll just solve for x, so let's divide both sides by 11. That leaves us with x equals 7.0 miles over 11.0 should be miles per hour. Our miles cancel, which leaves us with, for our units, 7.0 over 11.0 hours. So the hour now comes on top of the fraction or the numerator. So that tells us how long it takes for each runner to travel before they run into each other. Now that we know the time, we can then plug in x into either equation to figure out how far away from the flagpole they are when they hit each other. Let's just look at runner A. So y sub A equals 6 miles per hour times x, which is 7/11 hours, minus 4.0 miles. Plug in, chug in our calculators, and we get y sub A equals negative 0.18. It's an 8 miles. So that means that they ended up hitting each other to the left of the flagpole by 0.018 miles. If we wanted to use a physics equation for this, with two physics equations, we could have done the average velocity is a change in distance over the time. Multiply both sides by t, so the average velocity is a change in distance. Delta anything is final minus initial. So average velocity times time would be d sub f minus d sub I. We want to find their final position. So if we add d sub I to the other side, we get d sub f equals average velocity times time plus the initial position. That's the exact same equation that we have as y equals mx plus b. We're just using physics variables instead of math variables. Okay, that's number 19. The next question we'll do is number 30 something. 32. An object moves with a constant acceleration of 4 meters per second squared. Before I continue reading, let me make one of our charts that we have. VF, we'll leave space for units, meters per second. VI, meters per second. This looks like a constant acceleration problem, so we're going to use this chart. VF, VI, acceleration, meters per second squared, distance, meters, time, seconds. An object moves with a constant acceleration of 4 meters per second squared over a time interval, reaches a final velocity of 12 meters per second. We're given the acceleration is 4 meters per second squared. The final velocity is 12.00 meters per second. I probably should have started with, you don't have to change this, but VI, then VF. Not a big difference, but 12.00 meters per second. 12.0 meters per second. Question A asks, if the original velocity is 6 meters per second, that's the initial, what is its displacement during this time interval? So we want to calculate the displacement. We look at our formulas. We know VF, VI, VF, A, and we're finding D. The equation we'll use is VF squared equals VI squared plus 2AD. This is all the variables that we know and the one variable we're trying to solve for. So let's isolate the displacements. We'll subtract VI squared from both sides, divide by 2A to give us the displacements. From here, we plug and chug. 12.0 meters per second quantity squared minus 6.00 meters per second quantity squared, all over 2 times 4.00 meters per second squared. We plug this in our calculators and we get 13.5. And if we look at our units, when we square 12, we also have to square the units. So on the top, we'd have meters squared, all over meters per second squared. We can see that the second squareds go away, they turn into 1. And that leaves us with meters squared divided by meters. We can get rid of the square, get rid of the meter on the bottom, and that leaves us with 13.5 meters. Thank you for watching this video. I hope you found it useful, and I'll see you next time. See ya!